So, of course, the most high-profile development these days has been large language models like GPT. And sometimes they work really, really well. So here is an example of GPT-4, which is OpenAI's most advanced large language model, actually solving a problem from the IMO, the International Mathematical Olympiad. And so it's a question, there's a function that obeys a certain functional equation. Can you solve for the function? And it actually happens to give a completely correct proof. Now, this is an extremely cherry-picked example. I think they tried, from this paper, they tried all the recent IMO problems, and they could solve like 1% of the problems of this method. Famously, it's bad even at basic arithmetic. You ask it to solve 7 times 4 plus 8 times 8, and it'll give you the wrong answer. It gives you 120, and then it will keep going and say, and I'll explain why, and during the course of the explanation, it will actually make a mistake. And then you point out that they made a mistake and say, oh, I'm sorry, the previous answer was incorrect. I mean, these large language models, they remind me a lot of, if you have sort of a somewhat weak undergraduate student in office hours and you ask them to solve a problem at the blackboard with no aids, he or she will try their best, and try to generate something that looks like a proof. But they don't really have a good way of correcting themselves. So sometimes they work really well, but often they're very, very unreliable. But there's lots of interesting recent experiments where you can couple these language models to other much more reliable tools to do mathematics. So for example, GPT now comes with plugins for Wolfram Alpha. So now if you ask Wolfram GPT to do an arithmetic calculation, it knows better than to try to do it itself. It will outsource it to Wolfram Alpha. Then there are more recent examples where people are coupling these large language models to a proof verifier like Lean. So you ask it to prove a statement, prove that the union of two open sets is open. If you ask a raw large language model, it will give you the statement a proof that looks like a proof, but there's lots of little logical errors in the proof. But you can force it to output in Lean, get Lean to compile, and if there's a compilation error, it will send back the error to the large language model and have to correct it and create a feedback loop. And it can actually be used to solve roughly sort of undergraduate math homework level problems by this technique, but now with 100% guarantee of accuracy, if it works. I mean, of course, sometimes it will just get stuck and give up because it can never get the Lean compiler to accept the argument. But it is beginning to make some headway. As I said before, I do find it can be useful as a muse, kind of like if you're just starting on a project. I recently was trying to prove some combinatorial identity, and I was thinking of using. I had some ideas in mind. I was going to use some asymptotics, work with some special cases, but nothing was working. And I asked GPT for some suggestions, and it gave me some suggestions I was already thinking of, plus some suggestions that were either completely vacuous or wrong. But it did tell me that you should probably use generating functions, which I should have known. But at the time, it escaped me. And just with that hint, I was able to actually get the thing to work. So I mean, as just kind of someone to sort of double check your thought process, it is sort of useful. It's still not great, but it has some potential use. There was another tool which I do like, and I use more and more now. It's integrated into something called VS Code, which is an editor to write code, but it can also be used for LaTeX. Something called GitHub Copilot. It's basically an AI-powered autocomplete. And you type in your code or your LaTeX or whatever, and based on all the text that you've already written, it will suggest a possible new sentence to generate. And so it can be very useful for code. You write down 3 lines of code and you suggest the 4th, and sometimes it'll get exactly right, sometimes it's not exactly right, sometimes it's complete rubbish. But then you can accept it, and it can save a lot of time, especially if you're doing some very menial code where you're repeating something over and over again. It works for LaTeX. I wrote a LaTeX blog post actually recently where I was trying to estimate an integral. And I broke up the integral into 3 pieces. I said, okay, the first piece I can estimate by this technique, and I wrote down how to estimate this technique. And then the Copilot has just suggested how to estimate the second term, and actually a completely correct argument. It was just it was a modification of what I had already written. So it's very good at just modifying text that you've already appeared, and it's slowly being integrated into proof systems like Lean. So it's to the point where sort of 1-line proofs, 2-line proofs, we can kind of get the AI to fill in for us. The kind of steps that correspond to, like, this is obvious, or clearly this is true in a paper proof. I mean, not all of them, but we can get to the point where the AI can fill in a lot of them, and that will make proof formalization a lot faster. So there's a lot of potential. A lot of these technologies are very, very close to prime time, but not quite. It's still like, it took me a month to learn Lean and so forth. They're still not completely usable out of the box, but they are beginning to be more and more useful, and in surprising areas. You wouldn't have expected, say, knot theory to benefit from these tools, but they do. They can't solve math problems on their own, except maybe undergraduate level homework questions, maybe is the current level. But as an assistant, I think they can be very, very useful. They can generate conjectures. They can uncover connections that you wouldn't normally guess. Once proof automation becomes easier and scales better, we may be able to do completely new types of mathematics that we don't do right now. Right now we prove things one at a time. I mean, we're still kind of craftsmen. We take one theorem and we prove it, and we take another theorem and we prove it. Eventually you could automate theorem proofs like exploring an entire theorem space, of millions of different statements, and say, which ones are true, which ones are obviously false, and you could explore the geometry of theorems themselves. I think that we're going to see a lot of different ways to do mathematics, and we're going to see a lot of different ways to make connections in fields that we don't currently. And it'd be a lot easier to collaborate and work in different areas of mathematics. Especially because you can use these tools to sort of compartmentalize all these tasks, all these big complicated projects into small pieces. And plus also these large language models actually will become very good at getting humans up to speed on any number of advanced mathematical topics. Okay. Again, it's still not quite there yet. I would say, if, for example, with proof formalization, it takes about 10 to 20 times longer to formalize a proof than to do it by hand. But it's dropping. And I see no reason why this ratio cannot drop below 1. Eventually, it will become faster eventually we may just explain all our proofs to GPT, and GPT will generate, it will ask questions whenever we're unclear, but then it will just generate the LaTeX and the Lean and stuff for us. And eventually, and check our work at the same time. So I think this is all in the future. All right. So thanks for listening. Yeah.
Thank you. That was lovely. I think we have a couple minutes for a few short questions.
Okay, sure. So one prediction that some people have bandied about advances with AI-assisted theorem provers is that we might enter a period where there's a proliferation of proofs for new theorems that are formally verifiable, but which we don't yet have the technology to translate into forms that are easily comprehensible by humans. Do you see this being an issue?
Well, it already happens. For example, this Boolean Pythagorean triples theorem. No human will ever read that proof. So, I mean, I think it's actually not that scary. I mean, we rely on big numerical computations already in a lot of fields of mathematics. Of course, we would still want to have a human understandable proof. But as the knot theory example shows, you can take a incomprehensible computer proof and still analyze it and extract out from it a human proof. So I think that will be one of the ways we do mathematics in the future is to clarify computer-assisted proofs and make them human understandable.
Thank you.
I'm going to ask you over there to ask your
Hello.
question.
My question is kind of speculative, but I wanted to ask your opinion on the role of human intuition going forward with this. Because a lot of what we talked about is formalization of human intuition into formal mathematics. I was wondering if you think that intuitive part of coming up with the idea for the proof itself could be automated in the near future.
Not in the near future. As I said, these large language models can generate things that resemble intuition, but it has a lot of garbage. At the very low level of proving like 1 or 2 steps in a proof, we can use these proof assistants to sort of only pick out the good intuition and discard the bad one. But what large language models are terrible at right now is is differentiating good ideas from bad ideas. They just generate ideas. So unless there's another breakthrough in AI, I don't think this is going to happen anytime soon.
Okay, we'll take one more question from this side.
So I was curious about the need for blueprints. Is it that the system doesn't know enough definitions yet, or is the proof space too big? Some combination thereof?
No, it's more of an organizational tool for the humans. Okay, so if you want to coordinate 20 people to work on the same project, no one person, like many of the people who work on these projects, they don't understand the whole proof. So you need some structure to split it up into really small pieces, really atomic pieces that are self-contained for individual people to work on. So it's not for the computer. The computer can compile anything. It's for the humans to break up a complicated problem into lots of easy pieces. Kind of like how division of labor works in like modern industries, like factories.